Our galaxy is racing through space at 2.2 million kilometers per hour. This is not a random drift, but a purposeful flow, as if caught in a river with a hidden source. The force behind this immense motion is known as the Great Attractor, one of the most profound mysteries in modern cosmology. By the end of this journey, you will know 30 secrets about this cosmic anomaly and the vast web of structures that shape our universe. We will uncover what lies in a region of space permanently hidden from our view and learn whether this mysterious pull spells doom for our home. What does it feel like to discover you are part of a story written in gravity on a canvas of unimaginable scale? This river was first mapped by pioneers who dared to question a static universe. In the 1970s and 80s, astronomers like Vera Rubin were already revolutionizing our view of galaxies by proving they were filled with invisible dark matter. But another group, later nicknamed the Seven Samurai, asked a different question. If we look beyond individual galaxies, do they move together? By meticulously measuring the velocities of hundreds of galaxies, they made a startling collective discovery. Our entire local group of galaxies, including the Milky Way and Andromeda, is not just drifting aimlessly. We are all sailing in the same direction, pulled by a force originating from a region in the constellations of Centaurus and Hydra. The evidence for this cosmic current was later etched into the oldest light we can see. The afterglow of the Big Bang, the cosmic microwave background, should be a near-perfect uniform glow in every direction. But it is not. It is slightly warmer in one part of the sky and cooler in the opposite direction. This dipole anisotropy is not a flaw in the universe's design. It is our universal speedometer. The hot spot is the direction we are moving towards, the cool spot is where we are fleeing from, and the temperature difference tells us our speed. That speed is almost impossible to comprehend, 2.2 million kilometers per hour. To put that in human terms, at that velocity you could travel from Earth to the Moon in about 7 minutes. Yet, despite this breathtaking speed, we feel absolutely nothing. There is no cosmic wind rushing past because everything around us, the stars, the gas, even the dark matter in our vicinity, is moving with us in this same immense flow. We are not passengers on a solitary ship. We are part of a fleet, an armada of galaxies all caught in the same gravitational current, swept toward a destination hidden behind the thick dust of our own galaxy's central bulge. This is the first secret. We are not still. We are not alone in our motion. We are in the grip of a river whose source we cannot yet see. But this cosmic river needs a source, a wellspring of gravity powerful enough to command the motion of entire galaxies. The second secret reveals that the Great Attractor is not a lone, monstrous object in the void. It is something far more significant. It is the hidden heart of our home. In 2014, a team of astronomers led by Brent Tully made a monumental discovery. They were not just looking at where galaxies are. They were mapping how they move, tracing the subtle flows and streams in the cosmos as if they were charting ocean currents from space. What they revealed was our true cosmic address, a structure of staggering scale they named Laniakea. This Hawaiian word means immeasurable heaven, a fitting title for a home that defies human comprehension. Laniakea is our supercluster. It spans 520 million light-years and is home to roughly 100,000 galaxies, including our own Milky Way. Picture every star you have ever seen in the night sky, then multiply that by billions, and then multiply that collection by 100,000. That is the scale of the city we live in. And at the gravitational center of this immeasurable heaven lies the Great Attractor. It is the core, the downtown, the central plaza towards which everything in Laniakea slowly, inevitably flows. The motion we detected is not a journey to some foreign land. It is a homecoming. Every galaxy in our supercluster is drifting toward this central point like water spiraling gently toward a drain, caught in the gentle but inescapable pull of the largest structure we have ever called home. Yet this central plaza of our cosmic home is shrouded in a perpetual fog. The third secret is a profound cosmic irony. The direction we are all flowing toward, the heart of Laniakea, lies directly behind the blinding core of our own galaxy. Astronomers call this the zone of avoidance, and it is the single greatest blind spot in our map of the universe. Look toward the constellations of Centaurus and Norma, and you are looking into the dense, crowded plain of the Milky Way. Here, the spiral arms are thick with billions of stars, vast clouds of interstellar gas, and immense lanes of dark, obscuring dust. This material acts like a cosmic smokescreen, absorbing and scattering the visible light from anything that lies beyond it. For centuries, telescopes pointed in this direction saw only the foreground of our own galaxy. The universe beyond was simply wiped from the record, a blank space on the celestial charts that fueled endless speculation. What monstrous thing could be hidden there? A supermassive black hole of impossible size, a concentration of dark matter so dense it warps the fabric of local space. The mystery was intensified because the most obvious tool for exploring the cosmos, the optical telescope, was rendered nearly useless. We were trying to find a lighthouse while standing in the beam of a searchlight pointed directly into our eyes. This galactic foreground did more than just hide an object. It concealed the true architecture of our neighborhood, making the Great Attractor not just a mystery of physics, but a puzzle of perspective. Our own home was blocking the view to our ultimate destination. To see what our own galaxy was hiding, we had to change our vision entirely. The fourth secret reveals how astronomers learn to peer through the dust with X-ray eyes. Visible light is easily blocked, but the universe sings in many wavelengths. When galaxies cluster together, the space between them is not empty. It is filled with a superheated plasma, a thin gas burning at millions of degrees. This incredibly hot material emits not visible light, but powerful X-rays. Satellites like ROSAT in the 1990s and later the exquisite Chandra X-ray Observatory were built to listen to this high-energy song. Pointed toward the zone of avoidance, their view was unobstructed. Galactic dust is transparent to X-rays. What these instruments revealed was not a single, overwhelming source of gravity, but a complex and crowded metropolis. The heart of the Great Attractor is a grand confluence, a gravitational knot where several of the universe's most massive structures meet. The Norma cluster, an immense gathering of galaxies, sits near the center. But it is not alone. It is flanked by other colossal clusters like the Centaurus cluster and the massive, distant Hydra cluster. Together, they form a supercluster within a supercluster, a dense region of unimaginable mass dubbed the Norma Supercluster. This was the critical reshaping of our understanding. The pull we feel is not from a lone, hidden monster. It is the combined gravitational might of an entire metropolitan area of the cosmos, a sprawling intersection of galactic superhighways where the density of matter is so great it bends the flow of everything around it for hundreds of millions of light years. The mystery became less about a what and more about a where, the specific geometry of mass in the most crowded district of our universal home. The true anchor of this cosmic flow lies at a specific point in that crowded district. The fifth secret pulls back the curtain on the Norma cluster, known in catalogs as a C03627. This is the core of the beast, the most massive single structure sitting directly at the gravitational heart of the Great Attractor. Its statistics defy easy comprehension. The cluster holds the combined mass of roughly 400 trillion suns, a number so large it loses all meaning. To grasp its scale, picture every star in our Milky Way galaxy. Now imagine a structure that contains the equivalent of over 2,000 Milky Ways, all bound together by gravity in a region of space about 10 million light-years across. This colossal knot of matter lies approximately 220 million light-years away from us, which means the light we see from it today began its journey when dinosaurs still walked the Earth. What we observe is not a serene, stable city of galaxies. The Norma cluster is a scene of violent and ongoing construction. It is classified as a rich cluster, meaning it is densely packed with galaxies and it is undergoing major mergers. Smaller groups of galaxies are falling into the core, their orbits disrupted, their gas stripped away in a process that will eventually see them absorbed. At the center of this chaos sits a monster galaxy, a CD or central dominant galaxy. This is the gravitational king of the hill, a giant elliptical that has grown fat by cannibalizing its neighbors. Through a process called galactic cannibalism, it uses its immense gravity to tear apart and consume smaller galaxies that stray too close, incorporating their stars, gas, and dark matter into its own vast halo. It is this concentrated, titanic mass, the Norma cluster, and its devouring central galaxy, that acts as the primary anchor for the local cosmic flow. The gentle drift of our supercluster is not toward an abstract point. It is toward the overwhelming gravitational well of this specific, roiling metropolis of stars and dark matter, the definitive downtown of our immeasurable heaven. But the Norma cluster is not the final destination. The sixth secret delivers a shocking twist in our cosmic journey. Our relentless flow toward the Great Attractor is merely a local chapter, a subplot in a story written on an even grander scale. Beyond the dense heart of Laniakea, deeper in the constellation Centaurus, lies a structure so massive it commands the motion of superclusters themselves. This is the Shapley Supercluster, the largest known concentration of matter in our observable universe. Its distance is almost incomprehensible, roughly 650 million light-years away. To visualize that, consider the light we see from Shapley today began its journey to Earth long before complex life first emerged in our planet's oceans. This is not just another cluster, it is a supercluster of superclusters, a titanic gathering of dozens of massive galaxy clusters, each one rivaling or surpassing the Norma cluster in scale. Its total gravitational pull is so immense that it does not just affect its immediate neighbors. It tugs on the entire Laniakea Supercluster, including the Great Attractor at its core. Think of it as a vast cosmic watershed. The Great Attractor is a deep valley where local rivers of galaxies converge, but that entire valley itself sits on the slope of a mountain range of unimaginable size, the Shapley Supercluster. The gravity from Shapley is pulling on the valley, which in turn pulls on all the rivers flowing into it. So, while we are drifting toward the downtown of Laniakea, that downtown itself is being drawn ever so slowly toward an even greater metropolis. This reveals a profound hierarchy in the cosmos. We are caught in a nested set of gravitational influences, like a series of ever larger whirlpools. Our local motion is just the innermost ripple, governed by a force that is itself obeying a command from something far greater and more distant. The true end of our line, the ultimate destination of this universal flow, may lie not with the attractor we named, but with the colossal, shadowy presence that pulls it from the depths of space. Yet this immense pull from Shapley is only half the story of our motion. The seventh secret introduces a force defined by its profound absence, a cosmic push from a place of almost nothing. For every great attractor in the universe, there must be a corresponding repeller to balance the equation. Our high-speed journey is not just toward something, it is also away from something else. Astronomers call this the dipole repeller, and it is the shadow to Shapley's light. While Shapley is a mountain range of matter, the dipole repeller is a desert of staggering scale, a billion light-year-wide region of space that is eerily empty. In this vast cosmic void, the density of galaxies is far, far lower than the universal average. It is a place of profound quiet where the gravitational fabric of the universe is not pulled taut by mass but left slack. And in the grand gravitational tug of war that governs cosmic flows, emptiness exerts its own powerful influence. Think of space as a trampoline. A heavy object like a bowling ball creates a deep dip, and nearby marbles will roll toward it. But if you have a vast, flat region with no weight at all, marbles will naturally roll away from that flatness downhill toward the nearest dip. The dipole repeller is that flat region. Its lack of gravitational pull is functionally equivalent to a push. We are not being physically shoved by this void. Instead, we are sliding down the gentle cosmic slope away from its emptiness toward the dense concentrations of matter like Shapley and the Great Attractor. This reveals a beautiful and counterintuitive symmetry in the architecture of the cosmos. The universe's large-scale structure is a tapestry woven from both thread and absence. The great walls and filaments of galaxies define the pattern, but the immense empty voids between them are just as critical to the design. Our motion, and the motion of every galaxy in our supercluster, is a precise vector calculated by the universe, a result of being repelled by a colossal nothing and attracted by a distant everything. The story of where we are going is irrevocably tied to the story of what we are fleeing. This intricate dance of push and pull could only be understood once we learn to see the universe in 3 dimensions. For centuries, our maps of the cosmos were flat, showing only where galaxies were in the 2-dimensional dome of the sky. To truly understand structures like the Great Attractor, we needed depth. We needed to know not just where a galaxy appears to be, but how far away it truly is. The key to unlocking this 3rd dimension was found in a simple shift of color. When a galaxy moves away from us, the light it emits gets stretched. Just as the sound of a passing ambulance siren drops in pitch, the light from a receding galaxy shifts toward the red end of the spectrum. This is redshift. By carefully measuring how red a galaxy's light has become, astronomers can calculate its velocity away from us and from that, its distance. It is a universal speedometer and odometer combined, etched into the very light of the stars. But to map the cosmos, you need more than a few measurements. You need millions. The first ambitious attempt to chart the cosmic neighborhood was the CFA2 redshift survey in the 1980s. It was a painstaking galaxy-by-galaxy endeavor, but its first slices of the universe revealed something astonishing. Galaxies were not scattered randomly like stars in the night sky. They were arranged in vast, thread-like filaments and immense, sheet-like walls surrounding enormous, empty voids. The universe had a structure, an architecture, and it looked like a web. This revelation demanded larger maps. Projects like the 2-degree field Galaxy Redshift Survey, or 2DF, in the late 1990s used robotic fiber optic arms to capture the light from hundreds of galaxies at once, compiling a catalog of over 200,000 redshifts. It was followed by the Sloan Digital Sky Survey, or SDSS, which began creating a definitive 3-dimensional map of the universe, eventually charting the positions and motions of hundreds of millions of celestial objects. The latest chapter in this cartographic revolution is the Dark Energy Spectroscopic Instrument, or DESI. Mounted on a telescope in Arizona, it can capture the spectra of 5,000 galaxies every single night. Its goal is to measure the redshifts of an unprecedented 40 million galaxies and quasars, creating the most detailed 3-dimensional map of the universe ever made. These monumental surveys have collectively unveiled the cosmic web in all its glory. They show a universe built from great walls like the Sloan Great Wall, filaments that stretch for hundreds of millions of light years, dense knots where clusters like Norma reside, and the cavernous billion light-year-wide voids like the dipole repeller. Within this vast, interconnected network, the Great Attractor is no longer an isolated anomaly. It is a major node, a bustling intersection where several of the universe's largest filaments converge. Our supercluster, Laniakea, is simply one of many such structures within this grand design. We are not just flowing toward a hidden mass, we are moving along one of the great highways of the cosmic web, traveling toward a gravitational metropolis that sits at a crossroads of the universe. Yet the cosmic web is woven with threads of staggering scale, some of which dwarf even our own supercluster. One of the most astonishing is the Sloan Great Wall, a filament of galaxies so immense it seems to defy the very idea of a uniform universe. Discovered in 2003 from data gathered by the Sloan Digital Sky Survey, this structure is not a dense knot like the Great Attractor, but a sprawling, sheet-like river of galaxies. It stretches for approximately 1.3 billion light-years, a distance so vast that light, traveling at its universal speed limit, would take over 1 billion years just to travel from one end to the other. To put that in perspective, if the Sloan Great Wall were a road, driving from end to end at the speed of light would take longer than the entire history of complex life on Earth. This is not a destination for cosmic flows, but a backbone of the local universe, a great wall in the truest sense. While the Great Attractor is a gravitational hub where matter converges, the Sloan Great Wall is a filamentary highway, a part of the scaffolding upon which the cosmic web is built. It represents a different kind of structure, not a point of immense pull, but a line of immense connection, linking clusters and superclusters across a mind-bending volume of space. Its discovery immediately raised profound questions for cosmologists. For decades, a guiding principle known as the cosmological principle has stated that on the very largest scales, the universe should look roughly the same in every direction, with matter evenly distributed. The existence of a structure as colossal as the Sloan Great Wall, along with the Great Attractor and the Shapley Supercluster, seems to challenge that assumption. How can the universe be uniform if it contains such blatantly uneven features, these titanic concentrations that stretch across a significant fraction of the observable cosmos? The answer lies in the definition of largest scales. Cosmologists argue that while these structures are unimaginably huge to us, they are still just threads and knots within a tapestry that is even larger. If you could zoom out far enough to scales of several billion light-years, these great walls and attractors would begin to blur into a homogeneous cosmic foam. Yet, the very existence of the Sloan Great Wall forces us to constantly refine our understanding of where that scale of uniformity truly begins. It stands as a majestic reminder that our maps of the cosmos are still being drawn, and that every time we think we understand the limits of size and structure, the universe reveals a new colossus waiting in the data. The universe's oldest light holds a faint, frozen memory of structures yet to be born. The cosmic microwave background, that afterglow from the Big Bang, is not perfectly smooth. Its tiny temperature fluctuations are a blueprint, a snapshot of the infant universe's density variations that would one day grow into galaxies, clusters, and superclusters. But the story does not end there. These massive structures, including the Great Attractor, leave their own secondary imprint on this ancient light as it travels across billions of years to reach us. This happens through two remarkable cosmic effects. The first is called the integrated Sachs-Wolf effect. As light from the CMB travels toward us, it passes through the evolving gravitational landscapes of the universe. If it flies through a deep gravitational well like that of a supercluster, it must climb out. In an unchanging universe, the energy lost climbing in would be regained climbing out. But our universe is expanding, and dark energy is causing that expansion to accelerate. This means the gravitational well actually becomes shallower while the light is still traversing it. The light climbs out of a shallower pit than it fell into, gaining a net amount of energy. To our instruments, this gain looks like a slightly warmer spot in the CMB sky, aligned with that massive structure. Conversely, light passing through a vast, empty void loses energy, creating a subtly cooler patch. The second effect is the Sunyaev-Zeldovich effect. Here, the culprit is not gravity itself, but the superheated gas that fills galaxy clusters. When CMB photons pass through this searing plasma, they collide with the energetic electrons within it. These collisions give the photons a tiny boost in energy, shifting them to a slightly higher frequency. This creates a distinctive shadow or distortion in the CMB at the cluster's location, but at specific microwave wavelengths. It is like seeing the heat haze of a distant city against a cold sky. Together, these effects are powerful tools for cosmologists. By meticulously scanning the CMB and looking for these subtle, patterned distortions, scientists can essentially weigh distant galaxy clusters without ever directly observing their stars. They can map the distribution of both normal matter and, more importantly, the dark matter that shapes these gravitational wells. This means we can probe the gravitational potential of regions like the Great Attractor indirectly by reading the scars they leave on the universe's first light. The CMB is not just a relic of the past, it is a cosmic film that has recorded the passage of every major structure it has encountered. In its faint whispers of warmth and cold, we find a hidden map to the gravitational giants that now rule the cosmos. The sheer scale of the Great Attractor presents a fundamental puzzle. When astronomers add up all the visible mass, the billions of stars in the Norma cluster, the glowing hot gas between galaxies, every shred of luminous matter, the numbers fall catastrophically short. There is simply not enough stuff that we can see to generate the gravitational pull that commands the motion of our entire supercluster. This glaring discrepancy points to the 11th secret, the true architect of the cosmic web. The overwhelming majority of the mass in the universe, and therefore the primary source of the Great Attractor's gravity, is completely invisible. It is dark matter. To understand its role, we must shift our perspective entirely. The galaxies we see are not the structure itself, they are merely the light strung upon it. Dark matter is the invisible scaffolding, the cosmic framework upon which everything visible is built. From the moment the universe began to cool after the Big Bang, dark matter was there. Because it does not interact with light, it was free to begin clumping together under its own gravity long before normal matter could. It formed vast, diffuse halos and an intricate network of filaments, a gravitational blueprint for the universe. Ordinary matter, the protons and electrons that make up stars and planets, was simply along for the ride. As the universe expanded and cooled, this normal matter fell into the pre-existing gravitational wells carved out by dark matter. There it could collide, heat up, and eventually coalesce into the first stars and galaxies. Every galaxy we see, from our Milky Way to the giants in the Norma cluster, is nestled at the heart of a much larger, invisible halo of dark matter. This means the Great Attractor is not primarily a gathering of galaxies. It is, first and foremost, a monumental knot in the dark matter web, one of the most massive concentrations in our local universe. The Norma cluster and its neighbors are just the visible signposts, the glittering evidence of a hidden, titanic mass that we can only detect by its gravitational influence. The river of galaxies we are flowing in is not being pulled by the lights we see ahead. We are being drawn by the immense, unseen anchor of dark matter that holds them all in place. The most compelling proof for dark matter did not come from a telescope pointed at a quiet corner of the sky. It came from a cosmic crime scene. Two massive galaxy clusters, each containing hundreds of galaxies, slammed into one another in one of the most energetic events since the Big Bang. Astronomers call this system the bullet cluster, and its forensic evidence forever changed our understanding of the universe's hidden mass. Here is what happened. When these two titans collided, the different components that make up a cluster behaved in startlingly different ways. The galaxies themselves, vast islands of stars separated by immense distances, are like swarms of bees. When two swarms pass through each other, the individual bees rarely collide. They simply fly past one another and keep going. That is exactly what the galaxies did. They passed right through the collision mostly unaffected, but the clusters are not made of galaxies alone. The space between them is filled with a superheated plasma, a thin gas burning at tens of millions of degrees. This gas is different. Its particles are packed much closer together. When the clusters collided, this gas did not pass through freely. It slammed together, creating immense shock waves and friction, heating it even further and slowing it down dramatically. So after the collision, we were left with a bizarre snapshot. The two swarms of galaxies had sailed ahead, now on the far sides of the impact zone. The vast clouds of hot gas detected by its brilliant X-ray glow were stuck in the middle, a pile-up of cosmic traffic. Then came the crucial measurement, using the phenomenon of gravitational lensing, where the mass of a cluster bends light from galaxies behind it. Astronomers could map the total mass distribution. They could weigh the entire system. The result was definitive and shocking. The overwhelming majority of the mass was not with the hot gas in the center. It was not even perfectly aligned with the visible galaxies. The mass maps showed two huge, invisible blobs of matter, each one precisely trailing behind a swarm of galaxies. This was the smoking gun. The true gravitational anchors of these clusters, the dark matter halos, had behaved just like the galaxies. They passed through the collision without slowing down because dark matter does not interact with anything, not even with itself. It is truly collisionless. The visible hot gas, the only part that interacts strongly, got left behind. This observation provided direct, undeniable evidence that most of the matter in the universe is dark and that it forms the underlying skeleton of cosmic structure. Now connect this to the heart of our story. The Norma cluster at the core of the Great Attractor is not a serene place. It is a scene of constant, violent mergers, with smaller groups of galaxies falling into its gravitational well. The dynamics revealed by the Bullet cluster are almost certainly at play there, on a grand and ongoing scale. As galaxies and their dark matter halos stream into the attractor, they are performing a slow-motion version of that cosmic collision. The dark matter, the true source of the pull we feel, slips through these mergers unaffected, piling up at the center of gravity. The hot intergalactic gas, however, gets shocked and heated, glowing in X-rays just as we observe. This means the immense gravitational anchor we are flowing toward is not a static lump of matter. It is a dynamic, growing nexus, its dark matter core becoming ever denser as the universe continues its work of construction, silently shaping the river that carries us home. Pinpointing the exact weight of this cosmic anchor is a scientific challenge of the highest order. The 13th secret reveals that the Great Attractor's true mass is a numbers game, one where the estimates vary wildly and the final answer remains frustratingly out of reach. Astronomers have several tools for weighing such a distant giant, each with its own strengths and blind spots. The first method listens to the chaos within the Norma cluster itself. By measuring how fast individual galaxies are zipping around inside the cluster, their velocity dispersion scientists can infer the total gravitational pull needed to keep them from flying apart. It is like watching cars race around a track. The faster they go, the steeper the banking of the track must be. This method suggests the core cluster alone holds the equivalent of several 100 trillion suns. The second method takes the temperature of the cluster's atmosphere. The superheated gas trapped between galaxies glows in X-rays, and its temperature is a direct gauge of the depth of the gravitational well it sits in. Hotter gas means a deeper well, which means more mass. This X-ray thermometer generally agrees with the velocity measurements, painting a picture of a truly colossal object. But the most elegant method comes from Einstein's playbook, gravitational lensing. The immense mass of the attractor warps the fabric of space-time, bending the light from galaxies that lie far behind it. By carefully mapping this subtle distortion, astronomers can essentially weigh the entire region by how much it bends light. This technique is powerful because it measures all the mass, both the visible stars and gas, and crucially, the invisible dark matter. Yet, even with these sophisticated tools, the numbers refuse to settle. Some studies suggest the Great Attractor complex has a mass tens of thousands of times greater than our Milky Way. Others push that figure into the hundreds of thousands. The uncertainty is not just a matter of measurement error, it is woven into the very nature of the problem. Our view is still partially obscured by the zone of avoidance, meaning we might be missing significant chunks of mass hidden behind the Milky Way's dust. More fundamentally, it is incredibly difficult to draw a boundary around the Great Attractor. Where does its gravitational influence end and the general flow of the entire Laniakea Supercluster begin? We are trying to weigh a specific mountain peak while standing on the slope of the entire mountain range. This ongoing struggle highlights a profound truth about our place in the cosmos. We are embedded within the very structure we are trying to measure, making the final calculation one of the most delicate and consequential puzzles in modern cosmology. But if we are all flowing toward this immense gravitational nexus, a terrifying question naturally arises. Are we doomed? Is the Milky Way on a collision course with the heart of the Great Attractor, destined to be torn apart in a cosmic cataclysm? The 14th secret brings a surprising and calming answer. No, we are not. The fate of our galaxy lies elsewhere, governed by a delicate balance of forces on different scales. While the gravitational pull of the Great Attractor is real and powerful, it is not the only actor in this play. The universe itself is expanding, and on the largest scales, that expansion is actually accelerating due to the mysterious influence of dark energy. This creates a cosmic tug-of-war. Locally, gravity wins, pulling galaxies together into clusters and superclusters like Laniakea. But on the vast inter-supercluster scale, dark energy wins, pushing these immense structures apart from one another over time. Think of it like this: you are in a boat on a wide, slow river, floating toward a powerful whirlpool downstream. That whirlpool is the Great Attractor. But the entire river is also situated on a vast, rising tide, the expansion of the universe. As you drift toward the whirlpool, the tide is lifting the entire landscape, potentially increasing the actual distance to that destination. Current calculations suggest this is exactly what is happening. The expansion of space between the great superclusters is likely stretching the fabric faster than our local gravitational flow can overcome. We are caught in the current toward the attractor, but the finish line itself is moving away. So, what is our actual destiny? Our future is written in our own local neighborhood. In about 4 billion years, the Milky Way will merge with our largest neighbor, the Andromeda Galaxy, in a spectacular dance that will create a new, larger elliptical galaxy often nicknamed Milkomeda. This merged galaxy, along with the rest of our local group, will continue its long, slow fall toward the center of our supercluster, but we will not reach the Norma cluster at the heart of the Great Attractor. Instead, our trajectory is part of a larger flow that will likely see our local group, and eventually the merged Milkomeda, become a satellite of an even nearer giant. We are far more likely to end up orbiting the Virgo cluster, the massive core of the Virgo supercluster, which is itself being drawn into the Laniakea flow. We are like a leaf floating toward a vast, spinning drain. We may circle the outer edges of that drain for eternity, but we will never actually plunge into the center. Meanwhile, the Great Attractor, Laniakea, and the titanic Shapley supercluster will continue their own immense gravitational dance, shaping the cosmos on a scale so grand our own story is but a minor subplot. Our doom is not a violent collision, but a gentle, eternal integration into the suburbs of a local giant, forever circling the heart of a home we will never truly reach. Our supercluster is not an island in the void. It is a continent on a larger world. To understand the full context of our motion, we must zoom out further than Laniakea, to a scale where even our immeasurable heaven becomes a single landmark in a geography of staggering proportion. This brings us to the 15th secret. Our local flow is part of an even larger current, guided by structures that make Laniakea itself seem like a neighborhood in a cosmic megacity. Astronomers call these the Great Filaments, the universe's true superhighways. Laniakea is just one segment of a much longer, winding filament of galaxies, part of a colossal complex known as the Pisces-Cetus Supercluster complex. This name describes a web of interconnected superclusters, a sprawling metropolitan region that spans over 1 billion light-years. Within this complex, Laniakea, the Virgo supercluster, and several other giants are all linked, like burrows connected by bridges of galaxies and dark matter. But the discoveries keep pushing the boundaries of size. In 2020, astronomers announced the detection of the South Pole Wall. This is not a wall of bricks, but a curtain of galaxies, a concentration of matter so vast it challenges our very definitions. It stretches for an astonishing 1.4 billion light-years, making it one of the largest contiguous structures ever identified in our cosmic neighborhood. Crucially, it lies just beyond the Shapley supercluster, and its gravitational influence appears to be entwined with the flows we have been tracing. The river that carries Laniakea toward Shapley may itself be part of a broader current shaped by this newly found Leviathan. This reveals a profound, almost fractal hierarchy to the cosmos. Start with our local group of galaxies, a small gathering. That group is a suburb of the Virgo supercluster. Virgo is a district within the far larger metropolis of Laniakea. Laniakea is a borough within the Pisces-Cetus megacity, and that entire megacity is likely just one component of the South Pole Wall, a continent-spanning structure. At every level, the gravitational context expands. The pull we feel is not from one source, but from a nested series of gravitational wells, each one larger and more distant than the last. Our journey is not a straight line to a single point. It is a spiral path down an ever grander cosmic watershed, where local streams feed into rivers, rivers into oceans, all flowing within a basin whose true size we are only beginning to map. This nested view of our motion forces us to ask a startling question. Where are we right now within this grand hierarchy of structures? The answer is the 16th secret, and it completely inverts our perspective. While we are being pulled toward immense concentrations of matter, our own home sits inside a profound emptiness. We are residents of the KBC void, a cosmic bubble of staggering scale. Named for astronomers Ryan Keenan, Amy Barger, and Lennox Cowie, this is not a perfect vacuum, but a region where the density of galaxies is significantly lower than the universal average. Picture the cosmic web as a vast sponge. The filaments and walls are the solid material, dense with galaxies. The voids are the holes. The KBC void is one of those holes, and it is enormous, spanning roughly 2 billion light-years across. Our Milky Way, along with our entire local group of galaxies, sits not on a busy street in the cosmic city, but out in the quiet, sparsely populated countryside. This fact has a subtle but profound implication for how we measure the universe itself. For decades, astronomers have used the Hubble constant to gauge the rate of the universe's expansion. It is a critical number, a fundamental parameter of cosmology. One primary method to calculate it involves observing distant supernovae and measuring how fast they are receding from us. But here is the catch. If we live in a local underdensity, a giant bubble, the gravitational landscape around us is unusual. The relative lack of mass in our immediate vicinity means there is less local gravity pulling back on the expansion of space. As a result, space within our bubble might be expanding slightly faster than the true global average. Think of it like being in a hot air balloon that is already partially inflated. Measuring the pressure inside your balloon might not give you an accurate reading for the atmosphere outside. When we look at distant supernova from within our bubble, we might be measuring a slightly inflated local expansion rate. This potential bias from the KBC void is now a serious point of discussion in one of cosmology's biggest modern debates, the Hubble tension. Different methods of measuring the universe's expansion rate are yielding stubbornly different answers. Some scientists wonder if our privileged and unusually empty viewpoint within this colossal void could be a piece of that puzzle. so our journey takes on a beautiful symmetry. We are simultaneously fleeing a vast repeller of emptiness, living within a different void of our own, and flowing toward the greatest concentrations of mass in our vicinity. Our story is not just about where we are going, but about the uniquely quiet neighborhood we are leaving behind, a quietness that may be whispering secrets about the fundamental expansion of all reality. Deep within that gravitational heart, a silent feast is taking place. The 17th secret reveals the Great Attractor is not just a static mass, it is a cosmic digestive system, a place where galaxies are consumed and transformed. At the center of the Norma cluster sits a true monster, a galaxy known as a CD galaxy. This central dominant galaxy is the gravitational king of the hill, and it has grown to its immense size through a process as violent as it is beautiful: galactic cannibalism. Imagine a dense crowd at the core of a cluster, with hundreds of galaxies whirling around one another at incredible speeds. The largest galaxy, with its deep gravitational well, acts like a cosmic vacuum cleaner. When a smaller satellite galaxy strays too close, the tidal forces become overwhelming. The smaller galaxy does not simply crash into the giant, it is slowly, methodically pulled apart. Its outer stars are stripped away first, forming long, shimmering streams of starlight that arc across the void like cosmic ribbons. These are tidal streams, the ghostly remains of a galaxy being digested. Over hundreds of millions of years, the satellite's core is finally absorbed, its stars, gas, and dark matter becoming part of the giant's vast halo. This feast does more than just make the central galaxy larger. It fundamentally changes the environment of the entire cluster. As the gas from the consumed galaxy falls inward at tremendous speeds, it can funnel toward the supermassive black hole that lurks in the CD galaxy's core. This influx of fuel can ignite the black hole, turning it into an active galactic nucleus, or a GN. And a GN is one of the universe's most powerful engines, capable of outshining every star in its host galaxy combined. It blasts out jets of radiation and particles at nearly the speed of light, carving through the surrounding intergalactic gas. This violent feedback is a cosmic regulator. The energy from the AGN heats the gas in the cluster, preventing it from cooling, collapsing, and forming new stars. It is a self-limiting cycle, a feast that eventually stifles further growth. So the Great Attractor is far more than a destination. It is a colossal workshop of galactic evolution, where mergers reshape structures, black holes are fed, and the very future of star formation is controlled. The gentle flow we are part of brings galaxies to this violent, creative forge, where they are either consumed or forever altered by the energy of the feast. Gravity's grand design, however, faces a universal adversary. The 18th secret reveals the ultimate counterforce to all this cosmic gathering, a shadowy presence that works against the very clustering that built the Great Attractor. This is dark energy, and it is not a force in the traditional sense. It is better understood as a property of space itself. Empty space is not nothing. According to our best theories, it possesses a fundamental energy, a kind of cosmic tension that causes the fabric of the universe to stretch. For most of cosmic history, gravity was the dominant player. It pulled matter together, forming galaxies, clusters, and the great filaments of the cosmic web. But roughly 5 billion years ago, something shifted. The universe had expanded enough that the density of matter dropped, while the amount of empty space, and thus the total amount of dark energy, increased. Dark energy became the dominant influence, and it has one primary effect. It causes the expansion of the universe to accelerate. This is the critical opposition. Gravity pulls things together. Dark energy pushes space itself apart. They are locked in a tug of war for the fate of everything, and the Great Attractor is a battlefield in this conflict. The immense gravitational pull we feel is gravity's local victory, a testament to its power to shape matter on scales of hundreds of millions of light years. Yet that entire structure, the Laniakea Supercluster itself, exists within an expanding space that is being stretched by dark energy. So while we flow toward the attractor, the absolute distance to other faraway superclusters is increasing at an ever faster rate. This leads to a profound and lonely future. Current models suggest that in tens of billions of years, dark energy's influence will become overwhelming. The accelerating expansion will grow so powerful it will begin to overcome even the local gravitational bonds that hold superclusters together. The great filaments of the cosmic web, the very highways that connect us to the rest of the universe, will start to stretch and snap. Laniakea will become an island, cut off from all other structures as the space between them expands faster than light can cross it. Eventually, the expansion will win within our own supercluster. Galaxies like our distant descendant Milky Way will find their gravitational ties to the Great Attractor severed. They will drift apart into an ever-darkening, ever more isolated void. In the most extreme projections, given enough time, dark energy could even tear apart galaxies, then solar systems, and finally the very atoms that make up all matter. The Great Attractor, for all its immense power, is ultimately a temporary structure in a universe whose fundamental rules favor dispersion over connection, silence over community, a vast and empty stillness over the bustling cities of gravity. But how can we possibly test our understanding of a universe we can only observe from a single point in space and time? The 19th secret unfolds not in a telescope dome, but inside the humming servers of supercomputers. This is the realm of cosmological simulations, where scientists build entire universes from scratch inside a box. They begin with a simple, elegant recipe. Start with the fundamental laws of physics as we know them, particularly Einstein's theory of gravity. Then, fill a vast, simulated volume of space with a virtual dark matter particle in every cubic megaparsec, a digital representation of the smooth, early universe. Add in the precise amount of dark energy and a dash of ordinary matter. Finally, seed this pristine soup with the exact pattern of tiny density fluctuations we see imprinted on the cosmic microwave background. Press Start and let the simulation run. The supercomputer calculates the gravitational dance of trillions of particles over billions of virtual years. What emerges is nothing short of magical. From that smooth beginning, a familiar pattern spontaneously arises. Filaments of dark matter stretch across the void, knots of mass condense into halos, and vast empty bubbles form between them. The cosmic web materializes on the screen. This is not a guess. Landmark simulations like the Millennium Run and the more recent Illustris TNG project have done exactly this, creating staggeringly detailed virtual universes that look, statistically, almost identical to our own. They do not just create a pretty picture, they make specific, testable predictions. When astronomers compare these digital universes to our painstakingly collected maps from surveys like SDSS, the match is profound. The simulations produce the same distribution of galaxy clusters, the same sizes of voids, and the same statistical likelihood of finding structures as colossal as the Sloan Great Wall. Crucially, they also generate massive gravitational attractors. In the virtual cosmos, vast flows of galaxies emerge naturally, directed toward dense nodes in the dark matter web that look and behave exactly like our Great Attractor. This is the ultimate validation of our cosmological model. We are not just telling a story about the universe, we have written the recipe, and when we follow it, the universe we know bakes itself into existence inside a machine. These simulations allow us to rewind and fast-forward time, to watch the Great Attractor form from a faint ripple in the early universe, to see which filaments of the web fed it matter, and to project its fate billions of years into the future. They turn cosmology from a science of observation into a science of creation, letting us run experiments on the cosmos itself. The idea of a hidden cosmic force pulling us toward an unknown destiny is a story written not just in physics but in human imagination. Long before astronomers confirmed the Great Attractor's existence, science fiction writers were drawn to the terrifying and awe-inspiring concept of a gravitational siren in the dark. In Stephen Baxter's acclaimed Flood series, the Great Attractor is reimagined not as a passive mass, but as an active, almost conscious engine of cosmic change. It becomes a destination for a desperate human ark ship, a literal endpoint that represents both doom and transcendence. The popular grand strategy video game Stellaris incorporates similar ideas, featuring mysterious galactic phenomena and gravitational anomalies that players can discover, turning the unknown pull into a gameplay mechanic of exploration and risk. These stories resonate because they tap into a primal human narrative. The Great Attractor is the ultimate unseen hand, a perfect metaphor for fate or a predetermined path written into the fabric of reality itself. It speaks to our fear of being insignificant puppets in a vast cosmic play, and yet also to our longing for a grand purpose, a final destination that gives meaning to our journey. This cultural mirror shows that the mystery of the attractor is more than a scientific puzzle. It is a modern myth, a blank canvas upon which we project our deepest anxieties and hopes about the universe. The science gives us the numbers and the maps, but the stories give those numbers a soul, transforming a gravitational anomaly into a character in humanity's oldest story, the quest to understand our place in the dark. The final proof of our cosmic cartography will not come from what we have already seen, but from what we are about to discover. A new generation of observatories is being built with one explicit goal: to finally lift the veil from the zone of avoidance and map the full architecture of the universe. Leading this charge is an instrument already at work, the EROSIT X-ray telescope. Orbiting 1,000,000 miles from Earth, its mission is to perform the most sensitive all-sky survey in X-ray history. Remember, X-rays pass straight through the dust that blinds optical telescopes. EROSIT is not looking at stars. It is mapping the superheated plasma that fills the spaces between galaxies in immense clusters. Every time it scans the hidden region behind our galaxy's bulge, it is essentially taking an X-ray of the Great Attractor's core, weighing the hot gas and pinpointing previously obscured clusters. Its data is already revealing thousands of new galaxy clusters and supermassive black holes, painting a dynamic picture of the violent, high-energy universe that shapes cosmic flows. But to see the galaxies themselves, we need different eyes. The upcoming Nancy Grace Roman Space Telescope, set to launch later this decade, will be a master of infrared vision. Infrared light has longer wavelengths than visible light, allowing it to slip between grains of interstellar dust. Roman will conduct vast surveys of the sky, and when it stares into the zone of avoidance, it will see the stellar light of millions of hidden galaxies for the first time, finally filling in the blank spots on our three-dimensional map. Perhaps the most ambitious project of all is not a telescope that sees light, but one that listens to the faintest radio whispers of the universe. The Square Kilometre Array, or SKA, will be the largest radio observatory ever built, with thousands of antennas spread across 2 continents. Its supreme sensitivity will allow it to detect the faint signature of neutral hydrogen gas, the most abundant element in the cosmos which permeates every galaxy. By mapping this hydrogen, the SKA will produce a census of galaxies so complete it will essentially render the zone of avoidance transparent. It will trace the cosmic web in exquisite detail, showing every filament and void, and allowing us to measure the gravitational pull of the Great Attractor and Shapley Supercluster with unprecedented precision. Together, these missions represent a coordinated assault on the last frontiers of our cosmic map. Within the next 2 decades, the mystery that began with a puzzling flow of galaxies will be solved not by a single revelation, but by a flood of data, giving us our first clear, unobstructed view of the hidden heart pulling us home. The universe's first sound left a permanent ruler etched into the cosmos. In its earliest moments, the universe was a seething, opaque soup of particles and radiation, a plasma so dense that light could not travel freely. Within this hot fluid, gravity tried to pull matter into clumps, while the intense pressure of radiation pushed back out. This push and pull created colossal sound waves, ripples of overdensity and underdensity that raced outward at over half the speed of light. Then, roughly 380,000 years after the Big Bang, the universe cooled enough for atoms to form in an event called recombination. The plasma cleared, light was set free as the cosmic microwave background, and those racing sound waves instantly froze in place. Their final positions became a cosmic fossil, a specific, measurable scale imprinted on the distribution of matter. This is a Barrian acoustic oscillation, a standard ruler woven into the fabric of space itself. That ruler is enormous, about 500 million light-years from one frozen ripple to the next. Today, we can see its imprint in the way galaxies are spaced. If you could take a snapshot of the universe on the largest scales, you would find that galaxies are slightly more likely to be separated by this specific distance than any other. It is as if the universe has a subtle, repeating pattern, like the rings in a tree trunk marking its age. This pattern gives cosmologists a tool of incredible power. Because we know the original physical size of the sound wave from fundamental physics, we can measure how much it appears stretched or compressed in the sky. If we see the pattern in a cluster of nearby galaxies, it looks one size. If we see the same pattern in galaxies much farther away, and thus seen as they were much earlier in time, it will appear larger because the universe has expanded in the light travel time. By comparing the apparent size of this ruler at different distances, we can measure exactly how the universe has expanded throughout its history. This is where projects like the Dark Energy Spectroscopic Instrument, DESI, come in. Its mission is to map the three-dimensional positions of tens of millions of galaxies and quasars. Within that immense map, scientists can detect the subtle, statistical overdensity of galaxy pairs separated by that 500 million light-year scale. By doing this at multiple cosmic epochs, DESI is constructing a movie of the universe's expansion, frame by frame. This data directly tests the influence of dark energy and refines our gravitational models of the cosmos. For our story, this means the Great Attractor is no longer just a destination we infer from our motion. It becomes a landmark within a precisely surveyed gravitational landscape. The BRO ruler allows us to measure the true geometry and mass distribution of the Laniakea Supercluster and the even larger structures that pull upon it. We can weigh the attractor's influence against the backdrop of universal expansion, understanding not just where we are flowing, but how that flow fits into the entire history of space itself. The echoes of the first sound are guiding us to map the last hidden corners of our home. The precision of our cosmic maps has revealed a troubling inconsistency. The expansion rate of the universe, a number so fundamental it is called the Hubble constant, is telling two different stories depending on where we look. This is the Hubble tension, and it represents one of the most significant puzzles in modern cosmology. On one side, we have the local universe. Astronomers use what are called standard candles, like Cepheid variable stars and Type Ia supernova. These are celestial objects with a known intrinsic brightness. By measuring how dim they appear from Earth, we can calculate their exact distance. Then, by measuring how fast they are moving away from us via redshift, we get a direct local measurement of the expansion rate. This method, refined over decades, gives us a specific number. On the other side, we have the ancient universe. We look back to the cosmic microwave background, the frozen snapshot of the infant cosmos. By analyzing the intricate patterns in that light, we can deduce the universe's ingredients, the amounts of dark matter, normal matter, and dark energy, and from that predict how fast it should be expanding today. This early universe method yields a different, noticeably slower expansion rate. The two numbers disagree by a small but stubborn margin, about 10%. This is not a measurement error. It is a persistent gap that suggests something is missing from our cosmological model, or that our view of the cosmos is somehow biased. This is where our journey through flows and structures becomes critically relevant. Could the very gravitational landscape we have been exploring, the Great Attractor, the Shapley Supercluster, the dipole repeller, and our home in the KBC void be skewing our local perspective? If we live in a local underdensity, a vast bubble where matter is sparser than average, the space within our bubble might expand a little faster than the true global rate. It is like measuring the current in a quiet eddy and assuming it represents the flow of the entire river. Our local standard candles, the supernova we use as mileposts, are all embedded within this unusual gravitational terrain. Their measured motions are not just from the smooth expansion of the universe. They are also subtly nudged by the gravitational pulls of nearby massive structures and the pushes from nearby voids. When we try to measure the pure expansion rate, these local flows contaminate the signal. The Great Attractor pulling us inward and the dipole repeller pushing us away are part of this local gravitational noise. If we have not perfectly accounted for all these motions, our local measurement of the Hubble constant could be slightly off. Some cosmologists wonder if solving the Hubble tension might require a radical rethinking of our place in the cosmic web. Perhaps we are not in a typical region after all, but in a uniquely quiet or dynamic neighborhood whose gravitational whispers are loud enough to distort our view of the entire universe. The mystery of where we are flowing may hold the key to understanding how fast everything else is moving apart. Our precise location in this hierarchy feels almost like a dream when written out as a simple address. Earth, the third planet from the Sun, orbits a star in the quiet suburbs of a vast spiral galaxy. Our solar system is embedded within a minor spiral arm called the Orion Spur, a branching lane of stars and nebulae on the Milky Way's outskirts. The Milky Way itself is a grand, barred spiral galaxy containing over 200 billion stars, and it is not alone. It is one of two dominant galaxies in a small gathering called the Local Group, which also includes the Andromeda Galaxy and about 50 smaller satellite galaxies. This entire local group is a tiny, outlying district of a much larger urban area known as the Virgo Supercluster, a collection of galaxy groups centered on the massive Virgo cluster. But our cosmic cartography did not stop there. We now know the Virgo Supercluster is merely an appendage, a neighborhood within an immeasurably larger structure. Our true home is the Laniakea Supercluster, a continent of 100,000 galaxies spanning 520 million light-years, and we are flowing toward its bustling downtown, the gravitational nexus of the Great Attractor. Laniakea itself is not an island. It is part of a still larger filament of superclusters, a thread in the cosmic web known as the Pisces-Cetus Supercluster Complex, which stretches for well over 1 billion light-years. And all of this, every star, galaxy, and filament we have ever detected, resides within our observable universe, a sphere of space nearly 94 billion light-years across, defined by the distance light has had time to travel since the Big Bang. This address is not just a list of names, it is a map of our journey, a nesting doll of gravitational belonging that shows we are simultaneously residents of a quiet street and citizens of a universe whose grandest currents sweep us along. This grand address is not just a map of location, but a story of influence. The immense flow we are part of does not simply move our galaxy like a leaf on a river. It shapes the very nature of our home, sculpting its history and determining its future in subtle, profound ways. While we are not yet in the violent downtown of the Great Attractor, we are already feeling the distant tides of its gravity, an unseen hand that has been guiding the Milky Way for billions of years. One of the most dramatic effects occurs in the dense urban cores of galaxy clusters. There, a process known as ram pressure stripping acts like a cosmic wind. As a galaxy plunges through the superheated gas that fills the space between clusters, this thin but incredibly fast-moving plasma acts like a hurricane-force gale. It does not blow away the stars, which are too tightly bound by gravity. Instead, it blows away the galaxy's fuel supply, the vast reservoirs of cold hydrogen gas scattered between its stars. This gas is the raw material for making new stars. When it is stripped away, the galaxy is effectively starved. Its star formation is quenched and it begins to fade, transforming from a vibrant, blue, spiral galaxy full of young stars into a red, dead, elliptical galaxy. This is the fate awaiting many galaxies that fall into the heart of the Great Attractor. But what about us out here in the quieter suburbs of Laniakea? Our influence is more subtle but no less real. We experience a gentler version called galaxy harassment. As our local group moves along its filament toward the supercluster core, it encounters other groups and stray galaxies. These gravitational interactions are not head-on collisions, but distant, repeated passes. Each close encounter acts like a gravitational tide, gently tugging and distorting the shapes of the galaxies involved. Over billions of years, this harassment can puff up a galaxy's disk, trigger bursts of star formation from compressed gas clouds, and even tear long streams of stars from their outer edges, creating the faint, ghostly stellar streams we now see around the Milky Way. Some astronomers believe the very layout of our satellite galaxies, the Magellanic Clouds and the dozens of smaller dwarf galaxies orbiting us, may have been orchestrated by the larger gravitational field of Laniakea. These tiny galaxies are like leaves caught in the wake of our motion, their distribution and orbits shaped by the same cosmic current that carries us forward. Even the grand spiral structure of the Milky Way itself, the beautiful arms that define our galaxy's portrait, may have been influenced or sustained by these gentle, large-scale tidal forces over cosmic time. So our journey is not a passive drift. It is an active process of construction and transformation. The river we float upon is not just moving us, it is carving us, preparing our galaxy for the denser environments that lie ahead in the unfathomably distant future. The immense pull of the Great Attractor rests on a fundamental assumption that our understanding of gravity itself is complete. But what if the rules are wrong? The 26th secret confronts a radical alternative. Perhaps there is no dark matter scaffolding the cosmos. Maybe, on the vast scales of galaxies and superclusters, gravity simply behaves differently than Newton or Einstein predicted. This idea is called modified Newtonian dynamics, or MOND. At its heart, MOND proposes a simple tweak. In regions where gravity becomes incredibly weak, like the outer edges of galaxies, the force of attraction strengthens slightly beyond what standard physics expects. This single modification was originally crafted to explain why stars at the edges of spiral galaxies orbit just as fast as those near the center, a phenomenon that otherwise demands invisible dark matter halos. For individual galaxies, MOND works surprisingly well, but the Great Attractor presents a far greater challenge. Can a modified law of gravity account for the motions of entire superclusters and the violent dynamics within galaxy clusters? When astronomers apply MOND to the scale of the Norma cluster, the results are mixed. The theory can explain some of the internal motions, but it struggles mightily with the sheer amount of hot, X-ray emitting gas we observe. That gas is searingly hot because it is trapped in an immensely deep gravitational well. In the standard model, that well is carved by dark matter. In a MOND universe, the gravity from visible matter alone must be strong enough to create that well and heat that gas to millions of degrees. So far, the numbers do not easily add up. The most serious test, however, comes from collisions like the Bullet Cluster. Remember, that cosmic crash showed the majority of mass, revealed by gravitational lensing, was separate from the visible matter. MOND must explain how the apparent gravity can be in a different location than the visible stars and gas. Proponents have developed more complex versions of the theory to address this, but these models often require adding new, exotic fields that begin to resemble dark matter in all but name. This is the heart of a fierce and ongoing scientific debate. The Great Attractor, with its colossal flows and dense cluster core, acts as a natural laboratory. It forces every theory of gravity to make a prediction. Does your model produce a gravitational river this powerful? Can it create a node in the cosmic web this massive? The standard model of cosmology, with dark matter and dark energy, currently provides the most consistent story from the smallest dwarf galaxy to the largest supercluster flow. Yet the very existence of such a profound mystery keeps alternative ideas alive and compelling. It reminds us that science at its frontier is not about defending dogma, but about relentlessly testing our descriptions of reality against the universe itself. The pull we feel may ultimately teach us not just about what is out there, but about the fundamental nature of the force that connects it all. Mapping the cosmos is more than plotting points of light. It is about tracing motion, revealing the hidden currents that carry entire galaxies. This is the cosmic flow field, a three-dimensional atlas of velocity that turns the static map of the universe into a dynamic movie. Instead of seeing galaxies as isolated islands, astronomers now chart them as arrows, each one pointing in the direction it is moving and showing its speed. When you plot thousands of these velocity vectors, a breathtaking pattern emerges. You no longer see a collection of objects, you see a river system on a universal scale. Delicate tributaries of galaxies, often small groups and clusters, wind through the voids. These tributaries merge into mighty rivers, great streams of hundreds of galaxies all moving in concert. And these colossal rivers themselves converge, flowing into the deepest gravitational basins. The most prominent of these basins in our neighborhood is, of course, the Great Attractor. The flow field shows our local group is not on a direct beeline to this target. We are on a spiraling path, caught in a vast, slow whirlpool that gradually draws everything inward toward that dense core. But the map does not stop there. Follow the arrows further, and you see the entire river of Laniakea itself bending, its course subtly shifted by an even greater pull from the distant Shapley Supercluster. This dynamic map is the ultimate tool for cosmic archaeology. Gravity is the sculptor, and the motions of galaxies are its chisel marks. By meticulously reverse engineering these flows, scientists can work backward. They can take the observed velocities and calculate the precise distribution of mass that must be causing them. It is a form of gravitational tomography, allowing us to weigh the unseen. The flow field confirms the immense mass of the Norma cluster, but it also highlights the contributions of every other cluster and filament in the region. It shows how the dipole repeller's void pushes us and how the surrounding walls of galaxies shepherd the flow. This river of galaxies is not a metaphor. It is a precise, measurable reality, a testament to the fact that we live in a universe that is never still, where every object is part of a grand gravitational choreography that has been unfolding for billions of years. The age of this gravitational giant is not a single date, but a story of construction that spans the entire lifetime of the cosmos. To understand when the Great Attractor formed, we must rewind time to the universe's first moments to a state of near-perfect smoothness. The seeds for all structure, from the smallest dwarf galaxy to the largest supercluster, were planted then as quantum fluctuations, tiny, random variations in density, were stretched to cosmic proportions during a period of hyper-expansion called inflation. These minute ripples in the fabric of reality were frozen into the young universe, imprinted as the faint temperature differences we now see in the cosmic microwave background. The regions that were ever so slightly denser than average held the gravitational potential to become the future homes of galaxies. The particular overdensity that would one day evolve into the Great Attractor was among these primordial seeds, a faint whisper of extra mass in the infant cosmos. For hundreds of millions of years, this whisper remained quiet. The universe was expanding and cooling, and dark matter was silently beginning to clump under its own gravity, drawing the invisible scaffolding of the cosmic web. Ordinary matter, still too hot and energetic, was dragged along. It was only after the first stars ignited and the first small proto-galaxies coalesced that the true construction could begin. The region destined to become the Great Attractor did not spring into existence fully formed. It grew hierarchically through a relentless process of mergers and acquisitions. Smaller dark matter halos hosting the earliest galaxies began to gravitate toward one another, drawn together by their mutual pull. They collided and merged, building larger and larger structures. Over billions of years, these mergers created the first galaxy groups, then clusters, and finally, the immense knots in the web we call superclusters. Cosmological simulations allow us to watch this epic construction project unfold. If we run a simulation focused on our local universe, we can trace the lineage of the Norma cluster back through time. We would see it begin as a dozen smaller clusters and groups scattered across a few 100 million light-years in the early universe. Like tributaries flowing into a river, these groups slowly converged. Dramatic mergers would have occurred along the way. Events that violently heated gas triggered frenzies of star formation and fed the central supermassive black holes. The core CD galaxy we see today is the product of this long history of galactic cannibalism, a cosmic monarch built from the remains of countless smaller kingdoms it consumed. Based on these models, astronomers estimate that while the seed is ancient, the core cluster we identify as the heart of the attractor likely took recognizable shape several billion years ago and has been growing in mass and influence ever since. This leads to a fascinating question. Are we witnessing the Great Attractor in a special, particularly active phase of its assembly? The evidence suggests we might be. The Norma cluster is classified as a rich cluster undergoing mergers. The presence of that dominant, cannibalistic CD galaxy at its center is a clear sign of a recent major merger or a series of ongoing ones. The hot, X-ray bright gas that fills the cluster is turbulent, indicating it has been recently shocked and stirred by incoming matter. Furthermore, our maps of the cosmic flow field show a coherent river of galaxies hundreds of millions of light-years long, all streaming toward this point. Such a coherent, large-scale flow implies the gravitational basin is still actively deepening, still gathering its suburbs. This makes the Great Attractor more than a destination. It is a living laboratory for structure formation. We are not looking at a fossilized relic of the early universe. We are observing a dynamic construction site, a place where the fundamental processes that build the cosmic web accretion, merger, and feedback are happening in real time on the grandest of stages. By studying its current violence, we are watching the final chapters of a story that began with a quantum whisper nearly 14 billion years ago. The sheer scale of this cosmic construction site can leave a human mind feeling utterly dwarfed. We have traced a river of galaxies 500 million light-years long, flowing toward a hidden nexus of dark matter and cannibal galaxies. Our entire planet, with all its history, life, and strife, is a speck on a speck, adrift in this immense current. This is the humbling truth of our cosmic address. In the face of such grandeur, our individual lives can seem vanishingly small, our achievements ephemeral against a backdrop of billions of years. The Great Attractor does not care about our civilizations, our art, or our wars. It obeys only the silent mathematics of gravity, pulling on masses we cannot see, in a narrative where 1,000,000 years is but a blink. This perspective is a profound and necessary corrective to our innate self-importance. We are not the center of the universe. We are not even the center of our own supercluster. We are residents of the quiet outskirts, passengers on a voyage whose destination we will never reach. To grasp this fully is to feel a deep, almost oceanic sense of insignificance. Yet within that very insignificance lies a counterpoint of staggering significance. Consider the source of this story. Every fact we have explored, the velocity of 2.2 million kilometers per hour, the X-ray glow of hidden gas, the frozen sound waves in the cosmic background was not delivered to us by some advanced alien civilization. It was not written in the stars for us to simply read. We, from our tiny speck of rock orbiting an ordinary star, figured it out. We built the tools to see in X-rays and radio waves. We wrote the equations of gravity and expansion. We constructed supercomputers to simulate universes. We painstakingly collected the light from millions of galaxies to map the river we are floating upon. The very ability to perceive our own smallness is a triumph of colossal proportion. That a species which once huddled around fires, telling stories of gods in the sky, could now chart the gravitational pull of a structure hidden behind the bulge of its own galaxy is nothing short of miraculous. It speaks to a curiosity that refuses to be bounded by our scale, an ingenuity that builds lenses to see across time itself. So while the cosmos humbles us, the act of understanding it ennobles us. We are simultaneously the insignificant passenger and the brilliant cartographer mapping the river. This duality is the heart of the scientific journey. It begins with wonder at the night sky, matures into the disciplined search for truth, and returns always to a deeper, more informed wonder. The story of the Great Attractor is not just a tale of dark matter and galactic flows. It is a testament to the human spirit's relentless pursuit to know its place, however small that place may be, in the grand architecture of everything. The ultimate secret dissolves the very idea of a destination. After 30 revelations, we must let go of the notion that the Great Attractor is a singular object, a final stop at the end of a cosmic highway. It is not a place in any permanent sense. It is a moment. It is a gravitational focal point in an endless dynamic process, a temporary node in the evolving cosmic web that has been under construction for 13.8 billion years. Its greatest lesson is not about a hidden monster in the dark, but about the universe itself as a living, changing entity. Think of a whirlpool in a vast, flowing river. The whirlpool is real. It has structure, power, and a clear center that draws everything toward it. But the whirlpool is not made of special water. It is an emergent phenomenon, a consequence of the river's flow, the shape of the riverbed, and the force of gravity acting on the water. The moment the conditions change, the current slows, the riverbed shifts, the whirlpool dissipates. The Great Attractor is that cosmic whirlpool. It is an emergent phenomenon born from the interplay of dark matter, dark energy, and the specific initial conditions imprinted at the birth of the universe. The dark matter formed the invisible scaffolding, the riverbed of gravity. Ordinary matter flowed into those pre-carved channels, lighting up as galaxies. The initial density fluctuations from the Big Bang determined where the deepest channels would be, and all of this unfolds within the expanding space driven by dark energy, which sets the ultimate tempo for the entire dance. What we call the attractor is simply the deepest part of the local basin right now, the point where several of the universe's largest filaments currently intersect. But it is temporary. In the past, this focal point was elsewhere as smaller structures merged to build this one. In the future, it will be different. As dark energy's influence grows, it may tear this nexus apart, or a larger merger may create a new gravitational heart. The river of galaxies we are in will eventually find a new course. This shifts our perspective from a static map to a cosmic movie. We are not flowing toward a fixed point on a chart. We are participants in a single frame of an epic film that has been running for billions of years and will run for billions more. The awe we feel, then, is not for a distant object, but for the process that creates such objects, a process of such scale and complexity that it turns quantum whispers into superclusters and simple laws into a tapestry of breathtaking beauty. The final secret is that there is no final secret, only an endless unfolding. Our journey of discovery does not end with an answer, but with a deeper, more resonant question. What other temporary wonders are being born in the dark right now on scales we have yet to dream of? From a single puzzling motion, we have traced a river of galaxies back to its source. We began with the startling fact that our galaxy is racing through space at over 2 million kilometers per hour, a current first detected in the subtle red shifts of distant starlight. That current led us to the hidden gravitational heart of our home, the Laniakea Supercluster, a continent of 100,000 galaxies where the Great Attractor serves as the downtown. We peered through the dust of our own Milky Way with X-ray eyes, finding not a lone monster but a bustling metropolis of colliding clusters. We then saw that this entire metropolis is itself in motion, drawn by the even greater mass of the Shapley supercluster while being pushed by the immense emptiness of the dipole repeller. This journey revealed the true architecture of our universe, a cosmic web of dark matter filaments where galaxies are mere lights upon the scaffolding, and where the accelerating push of dark energy silently battles gravity's pull for the final fate of all structure. The hierarchy is breathtaking, from our local group to the Virgo supercluster to Laniakea and out to the billion light-year filaments of the Pisces Cetus complex. Each secret unveiled a deeper layer of connection and scale, reminding us that our place is both insignificant and profoundly special, for we are the mapmakers of this immeasurable heaven. Yet, for all we have mapped, the most exciting chapters are still being written. The next generation of eyes is already opening. The EROSIT, a telescope, is X-raying the hidden sky. The Nancy Grace Roman Space Telescope will soon see through the dust with infrared vision, and the colossal square kilometer array will listen to the hydrogen whispers of every hidden galaxy. Within our lifetimes, the zone of avoidance will vanish from our charts, and the last blank spaces on the map of our local universe will be filled. The mystery that began with a peculiar velocity will culminate in a complete, unobstructed view of the cosmic river that carries us. We would love to hear which of these 30 secrets reshaped your view of the cosmos the most. Was it the realization that we live inside a colossal void, or the forensic evidence from the bullet cluster? Share your thoughts below. If you are drawn to these deep dives into the fabric of reality, subscribe and join us as we continue to explore the universe's greatest mysteries, one revelation at a time.